What stops a star from collapsing into nothing? Not hope, not chance. It's a silent war between gravity, pulling everything inward, and light, fighting to escape. Inside our sun, photons burst outward from the core like endless cannon fire, while gravity drags it all back down. This fragile balance is the only reason stars shine. But when the fuel runs out, the balance shatters. The star swells red, burns its last breath of helium, then falls quiet. Now the laws of quantum physics step in. Electrons slam together so tightly they create a wall of pressure. A white dwarf is born. Push harder, past the Chandrasekhar limit, and even that wall breaks. Neutrons rise to hold the line, creating the densest objects we know. But if the star is too massive, gravity stops playing fair. The collapse doesn't end. No escape, no light, only a black hole shadow. Stars don't just die, they transform. And right now, somewhere in the night sky, another star is preparing to choose its fate. In 1959, physicist Hans Buchdahl uncovered a limit hidden in the math of stars. No matter how dense they become, no realistic star can shrink closer than 9/8 of its Schwarzschild radius, the invisible boundary that defines a black hole. That sliver of difference might seem small, but it changes everything. It means real stars must always be bigger than black holes, their surfaces just far enough out to escape the abyss. For a time, this was comforting. Black holes were the only true monsters, stars would always stop short. But then came the question that cracked the door wide open. What if a star wasn't made of ordinary matter at all? What if exotic forms of matter stranger than neutrons, stranger than anything we've touched, could bend the rules, producing pressures beyond anything we know? Suddenly, the neat pattern broke. A new possibility appeared. Stars that look, act, and even feel like black holes, but aren't. Cosmic imposters, waiting in the dark. That question led to something even stranger, the idea of a star made not of matter as we know it, but of vacuum itself. Using the Tolman-Oppenheimer-Volkoff equation, physicists realized that if the pressure at a star's core was negative pulling instead of pushing, the math allowed for bizarre new objects. In one special case, the negative pressure and the positive energy density cancel perfectly. Gravity pulls, pressure pushes back, and the forces erase each other everywhere inside. The result? A gravastar, short for gravitational vacuum star. Inside, you'd feel nothing at all, no pull, no push, just pure weightlessness, as if floating in empty space. From the outside, a gravastar would appear almost identical to a black hole, its radius hugging the same deadly line. But unlike a black hole, it wouldn't have an event horizon. It could, in theory, whisper information back into the universe. A star made of nothing, yet capable of imitating the darkest something we know. So, how do we tell the difference between a black hole and one of these imposters? Black holes are defined by one thing, the event horizon. Cross that invisible line and nothing, not light, not signals, not even time can return. But a gravastar or any exotic ultra-compact star sits just outside that boundary. No horizon. No one-way trip. In theory, it could still emit light or radiation, leaking whispers of its existence. And when these objects collide, the difference becomes louder. Black holes merge with a clean, predictable ring down the last sigh of space-time. Exotic stars lacking horizons might ring differently, producing echoes in gravitational waves. LIGO and other detectors are now listening for those faint signatures. Yet even with this arsenal of tests, the truth remains slippery. Some candidates match the Schwarzschild radius to 40 decimal places. To us, they look exactly like black holes. But what if, just beyond certainty, they aren't? In 2023, a bold claim shook astrophysics. A team at the University of Hawaii studied massive black holes across the cosmos and noticed something uncanny. Their masses seem to grow at the exact same rate that dark energy should increase as the universe expands. The conclusion? These weren't black holes at all. They were gravastars, filled with vacuum energy, the very stuff driving cosmic acceleration. If true, every so-called black hole could actually be a hidden reservoir of dark energy, rewriting our picture of the universe. But the backlash was swift. Astronomers argued the data was misread. Theorists fired back, saying cosmic expansion shouldn't affect black hole growth in the first place. Debate raged. Were we staring at the biggest discovery since dark energy itself, or just a mirage born from messy numbers? For now, the idea sits in limbo, thrilling, terrifying, and waiting for proof strong enough to silence the skeptics. Betelgeuse, the colossal red supergiant looming in Orion, stunned astronomers when ALMA data suggested its surface was spinning at 5 kilometers per second. For a star that size, this is absurd, almost impossible. Stars that grow bigger should slow down, like an ice skater spreading her arms. Yet Betelgeuse seemed to defy the laws of physics. The first explanation was brutal: stellar cannibalism. Perhaps Betelgeuse once had a companion star and tore it apart, stealing its gas and its angular momentum, spinning itself up in the process. But then came a quieter, stranger theory. Maybe it's not spinning fast at all. Betelgeuse's boiling surface is a chaos of giant bubbles, convective cells the size of planets, surging and collapsing at deadly speeds. When blurred by distance, those patches of blue and red-shifted light could trick us into seeing rotation that isn't there. Is Betelgeuse truly a cosmic cannibal, or just an illusionist star fooling our eyes? On a quiet night in 1866, an amateur astronomer spotted something shocking in the constellation Corona Borealis, a new star blazing into view where none had been before. It wasn't a supernova, but something subtler, a nova. At the heart of the system lies a red giant and its greedy companion, a white dwarf. The red giant's swollen atmosphere leaks hydrogen, which the white dwarf hoards like stolen treasure. Layer by layer, the pressure builds until the surface ignites in a thermonuclear flash. The system erupts, brightening more than 1,000-fold. Then, just as suddenly, it fades. This is the Blaze star, a recurring nova that explodes roughly every 80 years. The last was in 1946, and in 2024, it is expected to erupt again bright enough to see with the naked eye. For a few nights, an ordinary point of darkness will become a firework across the heavens before vanishing back into obscurity. For decades, cosmologists have agreed the universe is 13.8 billion years old. That number comes from everything we can measure: the redshift of galaxies, the glow of the cosmic microwave background, the rhythm of expansion itself. It all points to the same beginning. But then along came a rebel, a star hiding just 200 light years away, nicknamed Methuselah. Ancient, metal-poor, and dim, it seemed to carry a secret. Careful calculations of its evolution suggested an age of 14.5 billion years older than the universe itself. How can something be born before the cosmos? Perhaps the models are off. Perhaps we don't fully understand how such stars burn through their fuel. Or perhaps our picture of the universe's timeline still has cracks. While most refinements bring the Methuselah star back within the cosmic limit, the fact it ever appeared too old is a reminder. Even the simplest questions, how old is everything, can still defy certainty. Hubble has revealed stars that seem to mock the rules of nature. Infant suns buried in nebulae hurl out jets of plasma like cosmic lightsabers, while dying, giants carve impossible shapes, spirals, rectangles, and echoes of light rippling through the dust around them. Each image is a glimpse of stars caught in moments we were never meant to see, fragile snapshots of creation and collapse. But step beyond our galaxy and the spectacle only grows darker. In NGC 4993, two neutron stars collided, shaking space-time itself and scattering gold across the universe. In the Tarantula Nebula, the brightest, heaviest stars ever found blaze so fiercely they are destined to end as black holes. And in 1987, a blue supergiant detonated in a supernova so powerful its rings still glow today, illuminated by the debris of its death. From Hubble's snapshots to cosmic catastrophes, these are stars that shouldn't exist, yet do, rewriting what we thought was possible.